Hi, welcome to our work. I'm Insu Kim, working at Samsung Advanced Institute of Technology and also studying at CAST. In this presentation, I'm excited to introduce our work, Controllable Blur Data Augmentation using 3D-Aware Motion Estimation. Motion blur is primarily caused by camera shake and object movement during long exposure times. The blind image deblurring problem aims to solve this by estimating both the sharp image and the blur kernel. However, this is an ill-posed problem, making it challenging to achieve high-quality deblurring results. To develop practical deblurring solutions, large-scale blur datasets are essential. However, capturing sharp and blur images of the same scene under low-light conditions is challenging. Some studies address this using dual-camera systems, but the dual-camera system is heavy and complicated to collect a large-scale blur dataset. Alternatively, we can consider data augmentation techniques, but existing research on this line has not been extensively explored. Camera and object blur basically arise in 3D space. Traditional methods focus on 2D non-uniform blur fields. This requires per-pixel kernel regression without any physically driven blur modeling, which is highly ill-posed. Our method considers 3D motions by estimating rotation and translation parameters, which significantly simplifies the problem and is grounded in the blurring process. Before we discuss the details of our method, we introduce some related works here. Kernel-based methods aim to generate sharp images by using estimated blur kernels. However, we can use these blur kernels for synthesizing blur images. In kernel-based methods, simply regressing simulated kernels often fails to produce realistic blur images. These methods primarily focus on estimating motions from a two-dimensional perspective, which limits their applicability to real-world scenarios because motions typically arise in three-dimensional space. Diffusion-based augmentation methods offer controllable blur synthesis and generate diverse blur scenarios. However, they require significant computational costs, making them impractical for real-time data augmentation during the deblurring training. Moreover, they depend on video frame-based data for training the blur synthesizer, which is not mainly available in blur datasets. So far, we discussed our motivation and related works. Here we point out that estimating 3D motion is essential for realistic blur image synthesis. In this case, there are two key challenges. First, motion estimation in 3D space is difficult because we only have two deblurred images with no explicit depth information. Second, achieving controllability in motion estimation is crucial for effective data augmentation. But how can we implement this? In this paper, we introduce a 3D-Aware blur synthesizer in order to generate various realistic blur images. Our core idea is to rethink how 3D motion is represented. Instead of directly estimating 3D motion, we break it down into 2D motion and a 3D residual component. Here we highlight that 3D residual components fully account for depth-related components. By directly estimating 3D residual components using neural networks, we can estimate 3D motion without requiring depth measurements. Additionally, we represent motion as a vector field, such that we can adjust vector amplitude and phase in order to control blur amount and directions. As a result, we can handle a wide range of unseen blur scenarios by randomly varying the blur intensities, directions, and scenes during the deblurring training. Our blur synthesizer consists of two main components: 3D-Aware motion estimation and blur image synthesis. First, we estimate 2D rigid motion parameters, which are converted into 2D parametric vector fields. Also, we estimate 3D residual non-parametric vector field. They are integrated into 3D-Aware vector fields. Using these vector fields, we can generate the corresponding scene images by using grid sampling and aggregate them to synthesize realistic blur images. Estimating 3D motion is challenging. Instead of directly estimating 3D motion using inaccurate depth information, we represent 3D motion as a combination of 2D transformations and 3D residual components. This means that if we directly estimate 3D residual components by using neural networks, we don't need explicit depth information for 3D motion estimation. Furthermore, 2D motion is estimated by rotation and translation parameters, which is a form of parametric vector field. On the other hand, the 3D residual component is a form of non-parametric vector field. We can take advantage of both reducing ill-posedness by parametric forms and effectively modeling 3D residual components by non-parametric forms. Given 3D-aware vector fields, we generate the corresponding scene images by grid sampling, and then aggregate multiple transformed scene images to synthesize a blur image. So far, we considered the case of camera motion. We can extend it to the case of object motion. The non-parametric vector field is initially designed for representing 3D geometry residual components, but we can also use it for estimating object residual components. Therefore, our blur synthesizer can handle 3D camera motions and object motions without further modification. The vector field modification introduces ambiguities, which produce implausible results and artifacts. As a result, the controllable blur synthesis cannot be achieved. To address this, we introduce ambiguity regularizations, which consist of Laplacian regularization and geometric regularization. The Laplacian regularization is to enforce spatial smoothness, while the geometric regularization helps make vector fields geometrically consistent. These regularizations allow for controllable blur synthesis. After training our blur synthesizer, we can use our blur synthesizer for blur data augmentation during the deblurring training. Specifically, we generate 3D-aware vector fields from any blur image. Then, based on these vector fields, we randomly adjust blur magnitude and direction parameters for blur control. Finally, we apply these modified vector fields to new target images, which ultimately produce a wide range of unseen blur images during the deblurring training. So this enhances the generalization ability of the deblurring model. Let's move on to the experimental results. We conduct experiments across various data sets and network architectures. As you can see in the table, the results clearly demonstrate that our blur synthesizer boosts deblurring performance across not only different network architectures, but also various data sets. In this slide, we demonstrate the effectiveness of our method in various experiment settings. In particular, as you can see in the top right table, combining parametric and non-parametric vector fields, which is our vector field setting, gives the best performance compared to the other forms of vector fields. We also present visual comparison results on real-world blur images. You can see that our method gives compelling results on real-world scenarios compared to the other methods. For more insights on the proposed method, we conduct more experiments and ablation studies. You can check our paper. Thank you.